In this video, I'm going to go over 8.3 power series solutions to linear differential equations. And just before I start solving problems or differential equations, I'm going to go over really quickly over singular points. So please read the information above, and after that, so you can pause, and after that let's take a look at the examples. So the first example says determine all singular points of the following equation. So in order to do that, I'm going to divide the equation by x squared and y by x squared, because that is the coefficient of the highest power. So I'm going to get y double prime plus 3 over x squared y prime minus 1 over x y equals 0. So basically, if we take a look at the functions that we get here, 3x squared and negative 1 over x, they are defined everywhere except when x equals 0. So what does that mean? It means that x equals 0 is a singular point. All the other ones are called ordinary points, and in all those ordinary points we can actually have analytic functions as our coefficients of y prime and y. So the same procedure is for the second example. We are going to divide by theta squared minus 2. So we are going to get y double prime plus 2 over theta squared minus 2 y prime plus sine of theta over theta squared minus 2 y equals 0. So theta squared minus 2 cannot be 0, right? Or I set it equal to 0 to find the singular point. So theta squared equals 2, theta equals plus minus square root of 2. This is a common mistake. Students usually forget to put both plus minus. So these are singular points. Now, based on the information that you just learned, I would advise you to actually pause the video and try to solve problem 3 on your own. Welcome back. So just take a look at the problem. We divide by sine of theta, and then we solve the equation sine of theta equals 0, because that will give us the singular points. The points that are now going to make our cosine theta over sine theta an analytic function. Okay, and now we are ready to actually solve differential equations where the solutions are in the power series form. If you think about, so find 4 non-zero terms in a power series expansion about x equals 0. That's nice. That's the nicest one. You can have x equals 2, 3, and so on. For a general solution to the given differential equation, y prime minus y equals 0. So let's do that. Let's say that y of x equals sum, as n goes from 0 to infinity, of a sub n x to the n. This is a power series, right, in general. So now I want to actually find out, right, so to figure out what a sub n are. So y prime of x, it's actually sum as n goes from 1 to infinity of a sub n times n x to the n minus 1, right? We differentiate pointwise, and if you want to actually double check that, you can expand this, and gives you the expansion of y of x is this, right? And if you differentiate, if this is y, y prime is a1 plus 2a2x plus 3a3x squared and so on, which is actually the same thing as the expansion of this one. So now I'm going to replace y and y prime into the equation. Let's call it 1 into 1, and let's see what we get. So I just replaced, and we should notice that there are two differences. First, x to the n minus 1 and x to the n in the second one, and the other one is here it starts from n equals 1 and here it starts from n equals 0. So the very first thing that I'm going to do is rewrite the first sum so that x is to power n. So right now we have x to n minus 1. I want it to be x to n. What does that mean? It means I actually want to add the 1, right? So what's going to happen, each of them is going to add a 1. So each of them are going to become n plus 1, and this one is going to become just n. And this term, to still generate the same terms that was generating when it started with 1, now that it's going to go to n, just to n, not to n minus 1, it started 0. So here, so while we add a 1 to every single term after the summation, we are going to subtract the 1 from the sum. So now it's going to be sum as n goes from 0 to infinity of a sub n plus 1 times n plus 1 times x to the n. And if you're still wondering what I did there, you can actually expand the sum and see if you're getting exactly the same terms as if you would expand, as if you would get if n equals 1. So let's just think, if n equals 1 in this summation, so I'm going to highlight the whole thing. In this summation, if n equals 1, the first term is going to be a sub 1 times x to 0. So when I replace n equals 0 in this term, am I going to get the same thing? A sub 1 times x to 0. Yes. And you can try to do the same thing for the next terms and double check if you get the same thing. So then minus, now sum as n goes from 0 to infinity of a sub n x to the n. I just copied the 2. So what happened? Well, by rewriting the first sum so that the power is x to the n, we ended up with x to the n, both of them, and we ended up with both of them started at n equals 0, which means we can compact this into only one sum, and it's going to be a sub n plus 1 times n plus 1 minus a sub n, everything times x to the n equals 0, right? I factor out the x to the n, but we were allowed to do that just because x was to the same power. We were allowed to do that just because n started at the same value. Now, remember, we learned property where if the called power series vanishing on an interval, and if you have a power series equal to 0 for all the x in the open interval, then each coefficient is going to equal to 0. So our coefficient, these ones, have to equal 0 so that the power series equals 0. So that means a sub n plus 1 times n plus 1 minus a sub n equals 0, which means I can write a recursive formula, a sub n plus 1, it's a sub n over n plus 1, where n starts from 0, right? And that's positive integer. So basically, what we did, if we consider, let's start, I don't have any values, right? I don't have any initial values. So I'm just going to say a sub 0 is the first one. A sub 1 is going to be a sub 0 over 1. Why is that? Because the next term is the previous term over n plus 1. So a1 is the previous term, a0 over 0 plus 1, which is just a0. a2 is the previous term over 1 plus 1, so over 2. But a sub 1 was a0, right? Equal to that. Now let me find another one. a3 is the previous one over 2 plus 1, which is 3. But a2, we found it to be a sub 0 over 2 over 3, which means a sub 3 is a0 over 6. And I can actually find a couple more. So a sub 4 it's a sub 3 over 4, but a sub 3 it's a sub 0 over 6, and over 4 is going to mean a sub 0 over 24. What did they want us to find? They wanted us to find the first 4 non-zero terms. So basically the terms are a naught, a naught, a naught over 2, a naught over 6, and I can go a little bit further and say a naught over 24. And it's an interesting problem because I guess we can go a little bit further than the problem. So you would stop here if you had to do this in my MATLAB, but we can discuss a little bit more. So the first term it's a naught, the second term it's a naught, and the third term is a naught over 2. A naught over 6, it can be written 3 factorial, so, and a naught over 24, it's 4 factorial. So I kind of notice a pattern and I can figure out the next terms. So basically our y of x can be written a sub 0, right, because it's like this, right? It starts at n equals 0, so it's a sub 0 x to 0, so x to 0 plus a sub 0 x to the first plus a sub 0 over 2 factorial x to the second plus a sub 0 over 3 factorial x to the third plus dot dot dot, and I can actually write it as a sub 0, I'm going to factor it out, and then sum as n goes from 0 to infinity of x to the n over n factorial. Let me see, I'm going to start plugging in numbers to see if it's right. If n is 0, I'm going to get x to 0 over 0 factorial. That is 1. And then if n is 1, I'm going to get x over 1 factorial. So I'm going to get the second term. If n is 2, I'm going to get x to the second over 2 factorial. So I'm getting all the terms. Now, if you check out a list of Taylor series or Maclaurin series, you are going to see that this expansion that we just got, it's a naught e to the x. So we're basically using series, we found out the solution to be a naught e to the x. Now let me check, because we've learned this before, right? With a different method, y prime minus y equals 0. How about we use separation of variables? So y prime, it's actually dy dt, or maybe I should use x, dy dx equals y. So I'm going to cross multiply, so it's going to be dy over y equals dx. If I integrate both sides, right, I'm going to get ln of absolute value of y equals x plus c. So y equals c e to the x. Did we get exactly the same thing? Yes, it's just instead of c, we are using a naught. So now, feel free to try and practice the next 2 problems on your own. I hope this helps.